Hello friends, Namaskar. I welcome you all to this our technical webinar on MAP modified atmosphere packaging. Just before, I would like to let you know that right now all the attendees are in mute. At the end of the session, I will set it unmute and then you can unmute yourself and put your questions. We will have it at the end of the sessions. So now we start. Modified atmosphere packaging, also popularly known as MAP. It's a subject which we don't see so many different places and we don't get so much of information easily, even though so many people are using MAP. So as a packaging professionals, we thought this is a gap in the industry, something which we should address and let everybody know more about MAP. So before we start, I think the way we will start, we'll start from the history, then moving to the definition of MAP, why MAP, and finally taking to the advantages and disadvantages. Anything what we have is always good side to it and bad side to it. In the sense, may not be that bad, but yes. Before jumping into the MAP presentation, a bit of disclaimer that this is a educational presentation, more for the knowledge, and there may be some errors or some brands may belong to somebody else, so we don't own it, logos, names, etc. It is more for the discussion purpose and as a guideline, and then everybody has to decide their own what to do, what not to do. So coming to this, imagine an earth with 90% nitrogen, 10% carbon dioxide and no oxygen. So what do you think what will happen? Will anybody or anything survive? I think the answer is obvious no. But why? Because all living beings respire and require oxygen for respiration, except aerobic microorganisms. Anaerobic needs CO2. So before I jump into MAP definition, MAP is not something very, very new. And the barrel candles started in 18th century, then Whirlpool Corporation doing something 1950, 1960s. So it's quite an old thing. And the why it has been popular because it has been successful in increasing the shelf life with the different techniques. So what exactly is MAP? As the name is suggesting, modified atmosphere packaging. So it is the enclosure of the food in a package in which the atmosphere inside the package is modified with respect to CO2, O2, N2, water, vapors, and trace gases. It's like this when we switch on the air conditioning at home and outside is very hot, but inside is cold with the help of the air conditioning equipment. So in a way, we are modifying the atmosphere and the building being the package. Same is the case here. When you have a product and you have a package outside and in between air, you replace with some different kind of gases. That exactly is the modified atmosphere packaging. And then CAP, controlled atmosphere packaging. It's a subset of MAP. Basically, when you're transporting something and instead of just the packaging, you make a full truck, a big truck, or whatever the area where you control the atmosphere, like a cold storage, Cold storage is another kind of control atmosphere, or so that is a control atmosphere packaging. But fundamentally, you do the same thing, that you modify the atmosphere. Then why MAP? The key reasons is MAP is to extend the shelf life, and then obviously reducing the food related hazards. And of course, there's a need to ensure product safety and quality. The additional factors, why really we need to extend the shelf life and the rest of the things, because they're changing eating habits. Somebody lives in the US, he comes to India, they want the similar food what they are eating in the US, or Indians are going to the US or Europe or wherever. So sometimes you want a home food or home fruit or vegetable. So that is where the map will help you. And obviously it gives you greater choice depending on the lifestyles and extended geographic market. So I think the factors are absolutely clear. MAP will help to maintain the quality, extend the shelf life of fruits and vegetables. What quality of fruits and vegetables that resulted in development of MAP? So that is where we'll come to now. This is something very, very important in principle to understand the foundation of MAP, that the best possible quality of any commodity exists at the moment of harvest only. So from the point on, quality cannot be improved, only maintained. So the best quality, or whatever you call it, at the time of harvesting, that is the quality. And after that, you cannot do anything. It has to be only maintained. So we should not be thinking just in case that MAP will improve the quality. MAP will only maintain the quality. And this is how it happens. If you harvest immature fruit, so this is how it will look. And then if it's a ripened, will be something like this, the second one. And over ripened is the third one. What you see is not looking nice. And we all enjoy eating fruits and vegetables more when they are fully ripened, then that is the time when there's a real taste. I think in general nobody likes immature and over ripened fruits or vegetables. Everybody loves fresh, and that is the whole thing everybody is talking. Whole marketing happens fresh, fresh, fresh. Factors that affect the quality of fruit and vegetables once they are harvested. It's a intrinsic factors and extrinsic factors. So you can see respiration, acidity, water activity, ethylene produce. These are the inherent to the product. You cannot do anything. So, but these are the important factors we have to keep in the mind when we are designing the MAP packaging. And then there are external factors like temperature, loss of water. In simple terms, respiration is oxygen plus sugar, which gives you carbon dioxide plus energy plus water. Unlike animals and microorganisms, fruits and vegetables respire even after harvesting. Once the animal is dead, he or she is dead. But not in the case of fruits and vegetables. Even if we cut the fruit half, some respiration will continue to happen. So this is the respiration. Post-harvest, oxygen plus sugar, and then that is what I explained before. There is generation of carbon dioxide plus heat, exothermic reactions. More through the graph. This is respiration rate and oxygen. If O2 concentration is too low, anaerobic respiration will occur. So that means microbes which are there, aerobic microbes, they will start growing. And this is the effect of CO2 on respiration rate. So less CO2, more respiration. Acidity. Acidity influences the type of the spoilage. Fruits and vegetables generally have pH which is less than 4.5. Sorry, the fruits have less than 4.5 and the vegetables generally more than 4.5. And accordingly, the issue with the botulinum and the growing pH is also related to water activity, AW, which is what is water activity? AW is the amount of water that is available to microorganisms. That is in the simple terms. And water activity is one of the most important factors in controlling the spoilage, which you can see. Many organisms, microorganisms, prefer water activity of 0.99 and most need and water activity higher than 0.91. Most of the bacteria, for example, do not grow at a water activity below 0.9, and most molds cease to grow at water activities below 0.8. So this gives us some clues. Fresh fruits and vegetables, water activity between 0.91 to 1, and when the water activity is between 0.91 to 1, that means they are more susceptible to growth of spoilage microorganisms is high. Relative humidity versus water activity. So if the relative humidity is higher, the water activity will be higher. In the sense, or either way you can look through the formula. RH equals water activity into 100. So this is the classical chart, very old. I think hundreds of places you might have seen it. This is the interaction between pH and water activity, which controls microbial growth in food products. So higher the pH, more water activity, more pathogens. So you can see how the things are happening. Bakery, fruits, animal, meat, different bacteria, just to give you an idea. Fruits and vegetables fruits are also producing ethylene. Ethylene is a growth stimulating hormone produced by some fruits as they ripen. And ethylene basically hastens the ripening, and there is also a color development. Damaged and diseased fruits and vegetables produce high levels of ethylene. Then external factors, temperature, excessive heat, which you can see can already denature the protein, vitamin loss, reduction in the moisture level, surface burning. And if at the other side, if we also have uncontrolled cold, which is again, that means the change in the temperature, so which has surface biting, skin rupture, and off flavor. Water loss. Water loss depends on the RH, relative humidity, temperature of the product, and product surrounding atmosphere and air velocity. You see, if the air is strong, windy, it may have a different impact. Effects of water loss, fruits and vegetables become shriveled, which you can see. Water loss represents saleable weight loss and reduced profit. So even though sometimes the fruit may be good, but the fruit has shriveled, and that there's a loss of water, and when the fruit is being sold by weight, then there's a loss of profit. And if we don't have complete control over these different factors, what will happen? This is what happens. You can see on in the modified atmosphere on the left, banana 9 days, and after 9 days, what happens? So different fruits, different pictures taken. Now, holding on to that thought, now let us see what happens in case of animal products and byproducts. In animal and byproducts, see in the case of fish, autolysis happens, oxidation happens because of external factors, microbial growth, spoilage. You can see how the color is changing. Raw meat, raw red meat, microbial growth and oxidation. Raw poultry, microbial growth, particularly of Pseudomonas and Achromobacter species, is a major factor limiting the shelf life of raw poultry. Fish and fish products. So MAP can be used to control growth of microorganisms and oxidative reactions, but has no direct effect on autolysis. So autolysis, we cannot do anything. It is an internal process. So preventive method to maintain the quality and extend the shelf life, the factors like oxygen levels and micro attack need to be controlled. And this is what MAP can do. Dairy products, this is what happens. And application of MAP. So now you can see so far what is going wrong when there's a change in the atmosphere. So how application of MAP can help, and what are the different types of MAP? MAP can be by the gas flushing. It could be a continuous method. Another method is vacuum. Again, you take all the air out, or skin packaging so that you don't have any impact of outside air, or compensated vacuum. Passive modification. That means you have a package in film outside which has got control permeability, so whatever gases go inside, they are under control. So this is what it is. If you look at the center, for the longer shelf life, MAP is used for better preservation, better hygiene. It could be with the help of gas mixtures, working with the air, controlling the temperature, and doing the vacuum, flushing with gases, etc. Factors deciding the quality of MAP food. I think I don't have to read all this, but you can see the internal factors is basically composition. Biotic factors, microbiota, positive and negative interaction in the food systems. Processing conditions, which are under our control, we can do a better control processing. External factors, storage conditions, temperature, humidity, MAP, etc. We can work on it. Then these are the different types of microorganisms: bacteria, yeast, molds. Food ecology. So you can see that all food products have their own specific group of microorganisms associated with them, which is called the microbiota. So it's not that way, there's only one type of microorganism. It could be different or combination depending on the food. It's like human beings have immunity. So I guess fruits and vegetables also have their own immunity too. And they're susceptible to some, susceptible to not. Then gases. The technology relies on gases that are safe, common, cheap, readily available, and usually not considered chemical additives. That is the principle behind MAP. So you could say these are typically the packaging gases. Normal atmospheric levels: oxygen 21%, carbon dioxide 0.03%, nitrogen 78%, argon 1%. This is just the top line. And of course, there are other gases also which you can see which have been tried time to time. But oxygen, carbon dioxide, nitrogen are the major gases used. Choice of gas or gas mixture. Different combinations of these gases are appropriate for different foods, which I told you that every fruit and vegetable has its own needs. So as a packaging technologist, we will have to work with the food technologists and find out what is the combination required for a particular fruit and vegetable, and accordingly the packaging has to be designed. Important behaviors to understand. We have to know the interactions between gas and food, what is the main reason for the deterioration, and that is how then it's like a diagnosis. And then only the preventive techniques can be worked. Oxygen. Oxygen is the most important gas used metabolically by both aerobic spoilage microorganisms and plant tissues. It takes part in some enzymatic reactions in food, including compounds such as vitamins and flavors. It stimulates growth of aerobic bacteria and inhibits the growth of anaerobic bacteria. It combines readily with fats and oils and causes rancidity. That's a problem. Oxygen permeates quite slow through plastic polymers. Then carbon dioxide. Carbon dioxide goes faster. So generally for these reasons, the oxygen levels are kept to the minimum possible, except when you need oxygen for the respiration. So once the respiration has come and food has ripened, then you don't really need it. Carbon dioxide, it has its own value, and if carbon dioxide is more than 5%, then it can inhibit the growth of broad spectrum microorganisms and also inhibits the growth almost in proportion to the concentration up to 50%. So we have to decide where do we want to use carbon dioxide. So you can see the impact of temperature on the effectiveness of CO2. It's doubles at the room temperature, and in the refrigerated conditions, it quadruples, Nitrogen, it's an inert gas, low solubility, both in water and in lipids. It is also used as a filler gas in MAP, so that you can reduce the if you are not able to, if you want to do the vacuum, and the whole package will collapse, though you will take the oxygen out, but which may not be good for the product inside because product may collapse. So in that case, typically it is done through elimination, that you replace the oxygen with nitrogen, and nitrogen being inert, you have no negative impact. And that's what it says, to keep the package from collapsing as carbon dioxide dissolves into the product. It is used to purge air from a package to achieve a sufficiently low level of oxygen to prevent aerobic microbial spoilage. Carbon monoxide, it is colorless, odorless, tasteless, and is effective as browning and microbial inhibitor. But the problem is it's quite toxic, and which can cause health problems on exposure, and that's the reason it's actually commercially unviable. Sulfur dioxide, again, that many people are hypersensitive, so it has been tested but not really popular. Other gases, nitrous oxide, helium, neon, argon, there's so many different. So when we are using the map, you can see this is with the normal layer at 8 degree and with the map 8 degree, how the shelf life improves, you know, from so this to this. So if you have and this to this, so you get just with the change of temperature with the same gas combination, you can with the combination of gases in the temperature, you can achieve good shelf life. Types of packaging. So there's a permeability you can see, and it depends the different type of packaging. The barrier films, they are designed to prevent the exchange of gases and are mainly used with non-respiring foods like meat and fish. Permeable film, F&B, fruits and vegetables are respiring products. So there is a need for the gases to transmit from and to the package. And that is the reason the films which are designed are called permeable films, hence like LDP, PVC, not much in use, EVA, OPP are not permeable enough for highly respiring foods like fresh cut product, mushroom and broccoli. So the different factors deciding the suitable packaging material, barrier properties, mechanical, transparency, sealing quality. Multi-layer packaging. So for the proper right barrier properties to have the different properties, a combination of multi-layer films are used. And materials used are different thermoplastic polymers. Depending on the property which we need, we use it. And there's different combinations possible. This is not an exhaustive list. This is just a few examples. The different leading laminates, the thermoformable base wraps, preformed trays, some of the matte packaging. This is, I think, on the cryovac. This is some of the rigid trays. This is the shrink film applied, leak-proof seal area, barrier film liner inside. This is some more pictures in the tray. Rigid trays. Different map packaging materials based on polyolefins, vinyl polymers, styrene trays, polyamide nylon, good gas barriers, especially oxygen, polyester, very high clarity, and others. Active map, when packaging needs an active further action, like for example, there is extra moisture which you want to take away, and the fruit is giving the moisture, so they could be or giving oxygen. So there is some chemicals are put, for example, for oxygen scavengers. They will absorb the residual oxygen, and they're quite efficient. And there is also a CO2 absorbers. So like this is the oxygen scavenger. So whatever the extra oxygen comes from tomatoes, it keeps absorbing, and iron in the presence of water, iron becomes iron oxide, and this actively works. So scavengers can be in the form of pouch, which has got a iron oxide inside, and you see those small sachets many times. You see, this is the difference. Now you can see this endive, this leafy vegetables. There's no map. Then there's a map, passive map. So this one is better. And active map. So this looks even better. This is after 7 days of storage at 20 degrees. Same way, CO2 inhibitors and emitters possible, especially for the bakery. For moisture control, the silica gel or activated carbon, zeolite, and the some cellulose and derivatives. You see, typically you see silica gel even if when you buy a suitcase, computers, computer bags inside, you see some silica gel bags are lying around because moisture is quite possible everywhere, so it keeps absorbing actively. So that is also kind of modifying the atmosphere. Ethylene inhibitors, because when the fruits and vegetables the emitting ethylene oxide, ethylene gas, and so these systems will remove the ethylene and they will slow the process and to maintain the color. And when you want to ripen the fruit faster, like suppose you are transporting banana from New Zealand to Chile, so maybe people will put immature banana and put some ethylene emitters so that during the storage, during the transportation, with the help of outside ethylene, it will start ripening. Because remember, fruits and vegetables, even after harvesting, continue to respire. So when you have a commodity inside, there are different possibilities. How do you want to work on it through different combinations? There are a lot of new developments are also into process. There are a lot of edible coatings are coming up that you do the coating on the fruit and vegetables, so shelf life is extended. And different non-traditional gases to modify the respiration of the product. Oxygen shock. This is how typically the map machinery looks. And you need a different kind of packaging material for this. So these are the converting requirements. Filling requirements, what kind of seal type, manual filling, automatic filling accordingly. What is the coefficient of friction to run the film, etc. Accordingly, the machines are selected. Different machine types. So the machine types are like changing the atmosphere by displacement, like putting the nitrogen and taking the oxygen out, evacuation, creating a vacuum, gas replacement, the flow wrap machine. It could be different kind of packaging material. It could be coax film, laminate, the polyester with PVDC, and anti-fog coatings, coated co-extruded polypropylene, etc. There's so many. Vertical form fill seal machine. So that is where the gas is pulsed. Like there are so many different. Some of them are Sandicare, Woodman, Rovema. Thermoform fill seal machine, Multivac, Mecaplas, GEA, and many more. Rigid bulk fill seal like gas replacement by evacuation. There's so many different companies like Barnard in France offers extensive range of vacuum and modified atmosphere packaging machines for the different products. Bulk aspects, application of map. These are some of the pictures which you can see by different packaging done with the help of map. Some I will not call the recommendation, some idea like for fresh meat, 30% carbon dioxide, 70% oxygen. So it gives color stability. And but when you use 100% carbon dioxide, it extends the shelf life. It's like vacuum packaging. And carbon dioxide plus nitrogen, then it will inhibit the myoglobin formation on the surface, but dilutes CO2, which needs to inhibit growth of spoilage bacteria. So different combinations have to be tried and seen. Fresh poultry, 20% carbon dioxide can be effective as 80% over 1 week storage. Fresh fish, so the different combination for non-fatty fish and fatty fish. Again, one has to try and check it for himself. So you could see effect of oxygen on seafood. Oxidation reduces the freshness, causes loss of organoleptic properties, aerobic microorganism development. That means reducing nutritional value, etc. Fresh fruits and vegetables. So today, non-perforated films which have the desired permeability characteristics are available, and we can use it. So this is how it is. You can see this is the open air. This is the normal bag. So normal bag is not really good. And then comes matte. You can see how good it is. Then this is another example. Another one, 4 weeks, air, 20% CO2. You see what the difference? 0 degree, 2.2 degree, 5 degree. So I guess this is the good one. Then 3.5 months storage, air, 5% oxygen, 15% carbon dioxide. Tomato, chili, peppers, apricot, strawberries. Then a lot of studies have been done in different places. Lemon, lychee, parsnip, banana, pomegranate, passion fruit, fig, mango. Mango picture has not come out very well, but yes, mango in big demand, so good. Cantaloupe, watermelon. These are the leafy, parsley, mint, coriander, rucola, okra, green onion, leek, cucumber, beans, bell pepper. So 4 days at 20 degrees. Broccoli. So this is some of the recommended storage conditions for vegetables and fruits, but one has to look at it where they are selling, what are the atmospheric storage conditions in that area, what are the transport conditions, and really how long the shelf life you need. This is another one. This is taken from the USD Agriculture and Marketing Service, US, Kansas State University. Cereal based food. So you could see here the use of CO2 inhibits the growth of bacteria. It acts as antimicrobial and anti-staling agent, which slows down the staling process and allows longer softness. Typical modified atmospheres in general. Some more proportion of gases in packaging. You could see baked products shelf life could be as good as 3 months if you have this combination. No oxygen here. The strawberries, you need some oxygen, 1 to 3%. Iceberg lettuce, you need some oxygen as well as carbon dioxide and then most of it nitrogen. Rat meat, cooked meat, you don't need any oxygen. Or poultry, no oxygen required. Oily fish, no oxygen. Quality testing requirements, because we are playing with the gases, so it is important we can analyze the gases inside. So there are different instruments are available, and then also to check the leakage. Traditionally, there are the destructive methods to test the leakage. There's a water bath, and then there is also residual oxygen meter, then rhodamin dye test. Micro leaks could be dangerous, and they can be as small as 10 microns. And there are companies who can do really analyze it, like Oxypack. This is Oxypack designed equipment, non-destructive equipment based on the ASTM vacuum decay. They can find out if there is a leakage or not. And the test is gas independent. So all packages can be tested, CO2, N2, or any other gas mixture, which is a very good thing. Then we can, of course, gases can be analyzed. This is some of the method comparison of everything is regulated. So there are some of the European regulations. Now coming to advantages of MAP. I think the one most important advantage is clear, that it extends the shelf life. So improve quality and presentation. So improved, actually it is the maintenance, the quality at the time of harvesting. So hygienic stackable packs, sealed and free from product drip and odor, little or no need for chemical preservatives, clear view of the product and all-round visibility. It reduces economic loss because you don't have to waste it. Whatever you cannot consume in, say, in Bangalore, you can sell it in Mumbai or New York or Munich or wherever, or Paris, Netherlands, I don't know. So that is advantage, you can go across geography. Disadvantage, yes, you will have to invest into the machinery, different gas combinations. So there will be, so that if you want to take it, additional cost as a disadvantage, then it's a disadvantage. Temperature control is necessary, and retailers and consumers have to be taught about it, because MAP does not do anything on the temperature control. And remember, once the pack is opened, then the benefits of MAPs are lost. It is as good as soon after harvesting. So this is normal atmosphere, another picture, normal plastic bag, and modified atmosphere bag. So imagine again the 90% nitrogen, 10% carbon dioxide, and say no oxygen approximately. Will anybody or anything survive? I think if you're using map, if not we, our food will survive. So the key points to remember: map can increase shelf life, slow microbial growth, maintain nutritional quality, slow browning. It cannot substitute for temperature control. It cannot stop microbial growth. It does not improve quality. It only maintains quality. MAP is not a cure-all. It is not the answer to all food packaging problems. MAP will generally improve freshness of food once packed, and its acceptable shelf life, but will still be affected by the original quality of the food being packed. So if the original quality is not good, MAP cannot do anything. Under which conditions the food has been stored. If you have done a good map, but if you throw the hot sun or dirty area, very cold area, very hot area, whatever, then map can, or temperature India sometimes, or on the Himalayan region, temperatures can go up and down. So the impact of temperature, map cannot do anything. So it must be used in conjunction with other preservation techniques. So to conclude, for a successful map, we need thorough understanding of requirement and desired results. Matching requirements to property. Once we know what exactly is required, then we have to match the requirements with the different packaging material and gas properties and decide the package. And then select the proper package or design the proper package, do the quality and testing. So these are some of the references which we have used. And this is packaging connections. Thank you. And now I will open the I have unmuted you all. Unmuted you all, so you can unmute yourself and ask the questions if you would like, or type into the chat box, and then we will answer it. Yeah. So any question? You will have to unmute yourself and then ask. Okay. So I think looks like there are no questions. So in that case, I would say thank you for participating and listening to us. In case you like it and you would like to buy the copy of the presentation, we will send you the link and then you can buy the PDF copy. for your reference. And we can also support you on the map machines, etc. from Bernard if you're interested. We will send you more details. And for anything, please be in contact with us as and when you want. Yeah. Thank you. Bye. Have a good day. Namaskar. Thank you.